Now our meeting is recorded, and after the lesson I will send you the link to the video. Well, the problem statement of interpolating or interpolating. Maybe Is it okay for you if I show you the presentation like this, not on the full screen? Okay. Well, let's consider this example. Suppose we have a table with some data. This data can be any data from any from any field. For example, it can be price of car, or maybe the price of the tickets for the plane, or it may be, for example, the number of people that live in United States. So in this table, you may see the population in thousands of people in the United States from 1940 up to 1990. Of course, this table is off, and now we have a data of the amount of people in 2010 and 2010 and 2020. But suppose that we have this data, and as far as the census of population is taken every 10 years, we don't know nothing about the years between. For example, in 1965 or 1995. We know only these data. And the question is how to provide a reasonable estimate of population in these intermediate years. For example, in 1995 or any other year. And predictions of this type can be obtained by using a function that fits the given data. And this process of fitting the data with some function is called interpolation. You may see that in this example, these points lies not in a straight line. So there is no line that pass through these points. But these points, the points can lie not near some line. These points, for example, can look like this. Or something like this. So, if this data comes from other fields. Well, again, the problem of interpolation is that we have data in the form of table. So these data can be I can draw this information on graph as a points. And the question is how to interpolate these data. And let me start our discussion from a very simple example. Suppose that we have just 2 points. For example, we have just 2 rows in this table. How to interpolate the data? Suppose that I have only 2 points. I have only 2 rows in this table. And how to interpolate the data? So I know something at this point, I know something at this point, but I want to know what is between this point. Can you suggest any idea how to interpolate the data? How to make an estimation? How to make an estimation at this point? Just divide by 2. Find the middle. But suppose that I want not at the middle point, but at this point. At this point that closer to the right point, that and not close to the and far from the left point. Okay, I tell you the answer later. How to interpolate the data. And before we consider some interpolation techniques, let's review some points from the algebra and mathematical analysis. And let's review what is a polynomial. We considered on the first lesson, and I tell you that very, very important class of functions is called polynomials. And I ask you to give me examples of polynomials, and you give me examples of linear polynomial or quadratic polynomial or cubic polynomial. Here on this slide you may see the general form of the polynomial of degree n. How many coefficients are there in this polynomial of degree n? No? How many coefficients? How many coefficients we should write? We should have to write a polynomial of degree n. Okay, it's hard. How to write a polynomial of degree 1? What is a polynomial of degree 1?
It's 0. It's 1.
No, 1 is a constant. I ask you about a polynomial of degree 1. What is the degree of polynomial? Number n is the degree of polynomial. How to write a polynomial of degree 1? What is it? Ax plus b. And if we follow this general notation, it will not ax plus b, but a1x plus a0. the polynomial of degree 1, P1 of x, I can write as A1x plus A0. A1x plus A0. And the power of x is a degree of a polynomial. If you don't know it, please take your pen and paper and write all of the things that I said. This formula and my comments, you should write it, because on the next lesson, next week, you will come here, I ask you, please write me the polynomial of degree 1. And you look to me and you, I don't know. Because you don't write nothing. This is a polynomial of degree 1. And the power of x is the degree of this polynomial. X is a variable, and the numbers a, yes, and n, here n equals to 1. I can write also x power 1. The lower index corresponds to the just index, the upper index corresponds to the power. Now, how many coefficients are there in this formula? One coefficient. Two coefficients. What coefficient? What coefficients? A. A1 and A0. Two coefficients, two numbers. If I take, for example, some concrete values of these coefficients, for example, 1, 1 and 1, I get the concrete form of the polynomial. Just, for example, P1 of x equals to x plus 1. Yes. So if I take some coefficient, well, I should. Yes. How to write polynomial of degree 2? Using this notation, using this general form. How to write a polynomial of degree 2? This is a polynomial of degree 1.
Yes.
How to write a polynomial of degree 2?
Add another
A2x squared plus A1x plus A0. Polynomial of degree 2, or quadratic polynomial. How many coefficients are there in this formula in quadratic, for quadratic polynomial? 3. Now let's come back to my question, to the first question. How many coefficients are there in the formula of polynomial of degree n?
Yeah. N.
No.
Yeah.
No. Please look to these examples. Polynomial of degree 1, 2 coefficients. Polynomial of degree 2, 3 coefficients. Polynomial of degree n.
N plus 1.
N plus 1, of course. Not n, but n plus 1. We have 3 coefficients for degree 2, 2 coefficients for degree 1, and in general, to define a polynomial of degree n, we should define, right, n plus 1 coefficients, n plus 1 numbers. if somebody tells me these n+1 numbers, a0, a1, a2, a3, and so on, an, I can take these numbers and I can write a polynomial of degree n. Very good. So we consider in details what is a polynomial and how to define a polynomial. And maybe one remark before we continue, that polynomial can be written in different forms. One polynomial I can write in many different forms. I can give you a very simple example. Let's take a particular case of polynomial of degree 1. Just, for example, like this. P1 of x equals to 2x plus 4. 2x plus 4. Is it a polynomial? Yes. What is the degree of this polynomial? 1. And now this notation corresponds to this general form. A1 equals 2, A2, A0 equals to 4. But I can write the same polynomial in different form. What form? How to write this polynomial, the same polynomial, but in different form?
2x plus
2x plus, okay, you just write 4 as 2 power 2. But I also can write it as 2 x plus 2. It will be the same polynomial, but in different form. And I can write infinity many number of notations for the same one polynomial. Well, and polynomials are a very important class of functions because of several good properties of these polynomials. First of all, the polynomial can uniformly approximate continuous function. The explanation is as follows. If I have any continuous function, not a polynomial, but any other continuous function, trigonometric function, exponential function, logarithm, any other function, this function must be continuous on a closed and bounded interval. In this case, there exists a polynomial that is as close to a given function as desired. So you can tell me any function, and after that I can look to this function and tell you a polynomial that will be very close to this given function. Do you remember such function like sinus? What is the graph of sinus? How it looks?
Sine.
Sine.
It's
something like this.
yeah, like a parallel.
No, not parallel, but something like this.
Yeah.
For example, if we take sinus, it can look like this.
Yes.
Well, it's trigonometric function. It's not polynomial. But if you tell me some interval, for example, from this point up to this point, this interval, and on this interval, I can tell you a polynomial that will be very, very, very close to this function. The polynomial in this form, polynomial of degree 3, 2, or 4, I don't know. But I know that this polynomial exists. And this very important fact is proved by so-called Weierstrass approximation theorem. I write you this theorem on this slide, of course, without any proof, just as a fact. And this theorem briefly summarizes that I already told you. Suppose that f of x is defined and continuous. So suppose that this is f of x, and f of x is defined and continuous on the interval from a to b, and for each epsilon greater than 0, there exists a polynomial p of x with property that f of x minus p of x smaller than epsilon for all x between a and b. I draw you the picture on a board, and also this picture is some analogous picture is here on this slide. What you can see here. So this is a graph of a function f of x, and this is a polynomial p of x. This is a polynomial. Of course, function and polynomial are different, but we are sure that the difference between the function and the polynomial is not greater than epsilon. So the polynomial, the graph of the polynomial will lie between f of x plus epsilon and f of x minus epsilon. So upper and lower bound, and the polynomial lies here between these upper and lower bound. And I can take the value of epsilon as small as desired. I can take it closer, closer, closer. Of course, in this case, we will have different polynomials. But this polynomial exists. Well, is it clear? Do you understand this point? So I can take the function, and after that I can write such polynomial that will be very, very close to this function. And our consideration of interpolation techniques, we start from the very simple case that called a linear interpolation. We come back to my question at the my first question. Suppose that we have just 2 points. suppose that we have this table, this or any other table, and we have only two rows, only two lines this table, and these lines will correspond to 2 points. The point x0 and y0, and the point x1, y1. We have 2 points, x0, y0, and x1 and y1. If we have 2 points, the answer for my question, how to interpolate the data is very simple. Because if we have 2 points, there is just one line that passes through these 2 points. And graphically, the answer is very simple from the graphical point of view. We should draw a line. Draw a line that passes through these 2 points. And after that, using this line, I can predict, I can estimate the value of the function at any point. If you tell me the point, somewhere here, I can tell you the estimation on this line. If you give me the points here, the estimation will be on this line, and so on. And the question is how to draw a line that passes through the given points. So we have a points x0, y0, x1, y1. We can suppose that f of x0 equals to y0 and f of x1 equals to y1. We know that there is only one line that passes through these 2 points, and the question is how to find the equation of this line, the formula. And here is the answer. Here is the answer on this slide, how to find a formula of this line. First, we should write 2 functions, 2 auxiliary linear functions, L0 and L1. L0 equals to x minus x1 over x0 minus x1. And L1 equals to x minus x0 over x1 minus x0. And after that, I can draw a polynomial. P1 of x equals to L0x times f of x0 plus L1x times f of x1. Let me draw the thing on the board. That P1 of x equals to, first I should take L0, x minus x1 or x0 minus x1 times f of x0 equals to y0 plus x minus x0 over x1 minus x0 times y1. I just write the same formula on board. Now, well, so if we have this formula, we can try to compute the value of this polynomial at the points x0 and x1. But before we compute it, let's answer a question. What is the degree of this polynomial? Of course, it's written on the board, it's degree 1, but why this degree is 1? Because this formula looks differently. It's not in a general form of the polynomial. Why the degree of this polynomial is 1? Can you explain why the degree of this polynomial is 1? Not 2, not 3. In this problem, x0, x1, y0, y1 are constants, some given numbers. And in this formula, we have only two variables, x here, and the degree of this x is 1, and x here. Also, the degree of this x is 1. That's why the final polynomial will be a polynomial of degree 1. After that, let's try to compute the value of this polynomial at the point x0, p1 of x0. Please compute the value of this polynomial at the point x0. Some suggestion is written here on the slide, but I ask you to do it manually. What can you say about the first term? This term, when x equals to x0. What is the value of the first coefficient, the first term in this formula? Yes, I ask you about this term. X minus x1 or x0 minus x1. But we should find the value of this term at a fixed, at some given point, x0. how to find the value of this term at the point x0. Substitute x0 as x. You should use x0 as the value of x to compute the value of these two terms. And what is the answer for the first fraction, for the first term? Just substitute x. Zero. You should x0. You should use x0 instead of x.
When x1 is equal to 1.
Yeah.
Again, x0 and x1 and y0 and y1 are constants. Do you understand this notation? Of course, 0. But if okay, cancel each other. 2 over 2. 2 over 2. 1, of course. It's 2 cancel 2, but the result is 1, not 0. I told you that the suggestion is written here. The result is 1. The first term, the value of the first term is 1. Yes, if you substitute x0, it cancel each other, and you have 1 times y0 plus, what about the second? You substitute x0. The second term will be 0 because 0 over some number, it's not the x1 minus x0, will be 0. Because you have 0 here. Plus 0 times y1. And finally, p of x0 equals to y0. And please carry out the same computation for x1. P of x1. Substitute x1. You will have similar situation when in the first term you will have 0 over something, and the value of the first term when you substitute here x1 will be 0. 0 times y0 plus, and when you substitute here x1, which cancel each other, and you have 1 times y1, and the answer is y1. So the same is written here. The same is written here on this slide, that the value of the polynomial at the point p0, sorry, the value of the polynomial at the point x0 equals to y0, and the value of the polynomial at the point x1 equals to y1. it means that P is a unique linear function passing through two given points, x0, y0 and x1, y1. And if you have some concrete numbers, x0, x0, x1, y0, y1, you can find an equation of line that pass through these points. This is a graphical interpretation. This is a graphical interpretation. It's the same that I draw on the board. I also should draw the graph of the function. Something like this. Suppose that we know 2 points, x0 and x1, x0 and x1, and we know the function values at these 2 points, y0 and y1. Of course, between these points, the function can look, we don't know how it looks. It may be like this. Extremely many functions can pass through these 2 points. For example, like this. Yes, it's also the function that's passed through these points. Or it may like this. This is another example of the function that passed through these points. But only one linear function that passed through these 2 points. And this linear function is a polynomial of degree 1, and we can find the equation of this linear function of this polynomial using this formula. And this linear function can be used as approximation to all other functions that pass through these 2 points. Of course, this line, this linear function, it can be bad approximation for this function, but for this one, for another function, it's more or less good, because this function lies somewhere near this line. Well, do you understand the main point of interpolation? We know just 2 points, and there are a lot of functions that can pass through these 2 points. But we don't know nothing about these functions, but we want to approximate it. And as approximation, we can use a line that passes through these 2 points. Well, to understand it better, I ask you to solve some example, some particular example. I can, yes, for this. Let's look to this table. Suppose that we know 2 points. xi and fi function values. Fi. And suppose that we know 2 points. X equals to 0, f of x equals to 1. X equals to 3, f of x, sorry, x equals 2, x equals 2, f of x equals 3. So this is x0, this is x1, this is y0, or I can write it y0 and y1. Suppose we have such table. Please find the polynomial of degree 1 using these particular data and this formula. Find the equation of line. Find the polynomial of degree 1. Find the polynomial of degree 1 using this initial information. This is a task for all the students. This is x0, this is x1, this is y0, this is y1. Please find the formula for the polynomial of degree 1 that interpolates this data. Well, you write the data. I can, if you want, I can show you again the formula for the polynomial, or the first column corresponds to point 0. Second column corresponds to the point number 1, so x0, x1, y0, y1. Please find a polynomial of degree 1 that corresponds to this data.
Swift — это частная структура.
Well, did you find? What is the answer?
1 is 1 is equal to 0 plus 3 is but
No. You don't understand the task. Your
I
answer?
found 1.
1. What is your answer? Okay, but I asked you to find not the values. These values. We know the value of the point 0 is 1, the value of the point 2 is 3. And yes, this is the answer. I asked you to find the formula for the polynomial. The formula how to find the value of the polynomial at any point using x. So these computations we perform just to compute the values at 2 points, x0 and x1. But the question is how to find p of x. How to find p of x. The formula for the polynomial, where x is a variable. X is a variable, but not a fixed value. Again, let's come back to the beginning of our lesson. We discuss about the general form of the polynomial. What is the general form of the polynomial of degree 1? a1x plus a0. And the question, how to find a polynomial, is a question how to find the coefficients a1 and a0. And this formula helps us to find these coefficients. So my task, this task is to find the coefficients a1 and a0 using this formula for the interpolating polynomial. You should substitute here x1, x0, y0, and find a1 and a0. Not at given points 0 and 2, because we know the values at the points 0 and 2. What is the formula for the polynomial? You should substitute here x0, x1, y0, y1, and find this formula.
Если бы вовремя все сделали, потом в историческом периоде пошли на операцию.
Good. X minus 2 over 6 minus 1. Right. And after that you should simplify it. Simplify it. X minus 2 over 0 minus 2 times 1. Substitute these values, simplify the formula. X1 is 2, x minus 2 over minus 3 times 1 plus x minus 0 over x, I write just x over 2 times 3. I substitute this values, and after that you should simplify this formula, and after simplifications, what will be the answer? X x plus 1. After all simplifications, the answer will be x plus 1. And for this problem, it's very simple to check the answer. Is it correct or not? How to check? You should substitute these values of x, and you should get these values of y. If you substitute 0, x equals to 0, this formula gives us 1. If you substitute here 2, this formula gives us 3. So our answer is correct. This answer is correct. It's very, very simple to check your answer. Just substitute these points. Okay? I think I should give you one more example, one more task. Let's take another 2 points. Let's take another 2 points. They're 2 second points. Let's take x 2 and 3, and y 3 and 2. X 2 and 3, and y 3 and 2. I take the 2 second columns of this table, x 2 and 3 and y 3 and 2. These 2 columns. And please find the polynomial of degree 1 using these values. 2, 3, 3, 2. Use the same approach. You get the answer in this form. So finally, you should find the coefficients a1 and a0. You should write a polynomial of degree 1 that pass through these 2 points. Well, we get the result. -6. Yes, it seems correct if you substitute these 2 points. You get 3, it's 3, you get check.
X plus 2.
X plus 2. No. Check your answer. X plus 2. X plus 2, if you substitute 2, is it 3, 2 plus 2? No.
No.
So this answer is wrong.
I mean, it's going to be X minus 5.
Minus x plus 5, or 5 minus x. Yes, this is correct answer, because if you check it, so this is wrong. Minus x plus 5. Minus x plus 5. Minus x plus 5, if you substitute these values of x, you get these values of y. Fine. The computations are not very hard. Just you should, yes, substitute and simplify correctly. Well, now I think you understand how to find a polynomial of degree 1 if you know 2 points. If somebody tells you 2 points, you can substitute these values into this formula and find their equation of line. And after that, you can approximate any value. For example, at the point 1, substitute 1 and you get approximation, and so on. But the line is not very good polynomial. Line is not very good approximation for the function. You see that if the function is look like this, or even like this, line is not very good approximation. And next half, the second half of our lesson, we consider how to find approximation, how to find a polynomial of degree 2 that approximates, interpolates the given data. So the second half of our lesson, we discuss about the approximation of a polynomials of degree 2. Now it's time for break. Let's have a 10 minutes break. Well, I turn on the camera and I turn off the microphone. Well, and after 10 or maybe 15 minutes, we continue our lesson. 8 students are here who connects to our meeting using Microsoft Teams. And now we have a break, and after the break we continue.
Руку взять. Скоро.
Okay, let's continue our lesson. Well, first half of the lesson we consider the simplest problem, linear interpolation. So how to find an equation of line, how to find a polynomial of the first degree that pass through two given points, x0, y0, and x1, y1. So this picture describes the situation. We have 2 points. We have a lot of function that can pass through these points, and we have only one linear function, only one line that pass through these points, and we find the equation of this line. And how to check the answer? Just substitute the points into equation of line. If you substitute x0 and you get y0, if you substitute x1 and get y1, the answer is correct. Well, but this case is a simplest case. Now let's consider more general case, more general situation. Let's consider a construction of polynomial of degree n that pass through n plus 1 given points. Our first case, we consider linear polynomial that pass through 2 points. Linear polynomial is a polynomial of degree 1. And for the polynomial of degree 1, we should know 2 points. And for polynomial of degree n, we should know n plus 1 points to find a polynomial. These n plus 1 points are x0, f of x0, x1, f of x1, xn, f of xn. And again, this picture illustrates the situation. We have a function, f of x. This is a graph of the function. And we know the values of the function at endpoints, x0, x1, x2, and so on, xn. And we are going to find a polynomial, p of x, that pass through these points. So actually I can say that we have a table of n plus 1 data points, xi, yi. So these points are x0, y0, x1, y1, and so on, xn, yn. And we seek for a polynomial p of x of a lowest possible degree for which p of xi equals to yi for all the points, for all number I from 0 to n. Such polynomial is said to interpolate the data, and p of x is called interpolating polynomial. And before we continue, I want to discuss about these two words. Polynomial p of x of lowest possible degree. And let me again draw the picture. Suppose that we have 2 points, x0 and x1, like in previous case, this point and this point. I told you that there is only one line, only one polynomial of the first degree that pass through these 2 points. But there are a lot of other polynomials that pass through these points. What is a graph of quadratic polynomial? Do you remember how it looks? Quadratic.
Yes. Quadratic.
Quadratic polynomial. No, it's not a quadratic polynomial. It's like a science.
Quadratic is like
No. Quadratic polynomial like this. Parabola.
Oh, parabola.
Yeah, parabola. Quadratic. The graph of quadratic polynomial. And I can find a quadratic polynomial that passes through these points. Something like this, right? So there is one line, so one linear polynomial that passes through these points. One, for example, or semi-quadratic, or even I can say that there is this a cubic polynomial. Do you remember the graph of the cubic polynomial?
Yes,
Cubic polynomial. Polynomial of degree 3. What is the graph of polynomial of degree 3? In general, so this is first degree, this is second degree, and this is the third degree. Looks like this, or like this. Something like this. And I can say that there is a polynomial of degree 3 that passes through these points. Something like this. So, I want to say that there are a lot of polynomials that pass through these 2 points. Linear, quadratic, cubic. But what polynomial have a lowest degree among all of these polynomials? Linear polynomial. It's a polynomial of lowest possible degree. And the problem of interpolation is not to find any polynomial, but polynomial of lowest possible degree that pass through these 2 points. Because I can say that there exists a polynomial of 100 degree that pass through these points. But this answer we cannot apply. We cannot apply it. We cannot find this polynomial. Yes, it exists, but we cannot find it. A lot of polynomials, but we are going to find a polynomial of lowest possible degree. And only this polynomial is called interpolating polynomial. And there is a theorem, very important theorem, so called interpolating theorem, that tells us that if the values x0, x1, and so on, xn are distinct real numbers. There is no the same numbers. All numbers are different. So if these values are distinct real numbers, then for any values y0, y1, yn, there exists a unique polynomial p of x of degree at most n, such that p of xi equals to yi for all I from 0 to n. This theorem tells us that if we have n plus 1 points, we can find a polynomial of degree n that pass through this point. For any different values. Well, let me try to explain the proof. Maybe to understand the proof of this theorem, the proof is very simple. Actually, the proof is very simple. But to understand that, you should remember some very simple points from mathematical analysis. Suppose that you have a polynomial of degree n. How many roots does it have? Polynomial of degree n. N plus 1 coefficients. Roots. What is root of a polynomial? Because we consider this problem just on previous lesson. What is the root of a function? What's the root of the equation? The points of intersection. The point of intersection with x. This is a polynomial of degree 2. How many roots? 2. Or maybe 1. Yes, if lines pass. Or no roots. If polynomial of degree 1, how many roots? 1. 1 point. If polynomial of degree 3, how many roots? If this line passes here, 1 root. But what is the largest number of roots? 3. 3 roots. If this line passes here, 3 roots. So the largest possible number of roots of the 0 points of a polynomial of degree n is n. For quadratic polynomial, 2 roots, cubic, 4 roots, polynomial of degree 4, 4 roots. It cannot be more roots than n. Polynomial of degree 3 cannot have 4 roots or 5 roots. It can have at least 3, at most 3 roots. No more than 3 roots. And this fact is the basis for this proof. Suppose that there are 2 polynomials, Pn and Qn. Yes, and on the previous slide, one of the statements of this theorem is that this polynomial is unique. It means that only one such polynomial not 2, not 3, but only 1. And first, let's prove unicity. Suppose that there are two such polynomials, Pn and Qn. So polynomial is not unique, and there are two polynomials. Let's consider polynomial Pn minus Qn. And this polynomial would have the property that P of xi minus q of xi equals to 0 for all the points from 0 to n. And since the degree of a polynomial can be at most n, this polynomial can have at most n zeros. I explain it for you. If it's not the zero polynomial. But since the numbers xi are distinct, then this polynomial Pn minus Qn has n plus 1 zeros. So it's a contradiction that this polynomial must have at most n zeros, but it has n plus 1 zeros. So it's a contradiction. Hence, our supposition is not correct, and Pn identically equals to Qn. It cannot be different polynomials. It can be just one polynomial. So Pn identically equals to Qn. So this is a proof of unicity. And the next part of this theorem, it's a proof of existence. So because this polynomial exists and unique. Now let's prove that this polynomial exists. Suppose that n equals to 0. N equals to 0. It means that we have only one point, x0, y0. And if we have only one point, the existence is obvious since a constant function, a polynomial of degree 0, can be chosen to interpolate the data. So that P0 of x0 equals to y0. Now let's suppose that we have a polynomial of degree k minus 1 with the property that pk minus 1 of xi equals to yi for all the points from 0 to k minus 1. So we take first k minus 1 points, and we build a polynomial using these points. Now let's try to construct a polynomial of degree k using the following form. This form is written on the slide. Let me reproduce this form on the board to explain it for you. Again, what is pk minus 1? Pk minus 1 is a polynomial of degree k minus 1 that interpolates first points 0, 1, 2, 3 up to k minus 1. And we consider one more point xk, yk. and we try to write a polynomial using this form. Pk of x equals to pk minus 1 of x plus some coefficient c. Actually, we don't know c. Right now c is just the coefficient c times x minus x0, x minus x1, and so on. And the last term is x minus xk minus 1. pk minus 1, suppose that we know. First of all, this polynomial is a polynomial of degree k, because this polynomial is a polynomial of degree k minus 1, and the last term has a power k. And moreover, pk interpolates the data that pk minus 1 interpolates. If we try to substitute here any point from x0 to xk minus 1, what can we say about this term? If I substitute here any point from x0 to xk minus 1. For example, let me take x1. pk of x1. I take x1, it's pk minus 1 of x1, plus, and I substitute here x1. What I get as a result? If I substitute x1 at the second term, if I substitute x1 here, zero. I get 0 plus 0, because this is 0. If I substitute x0, 0, x2, 0, x3, 0, for all x from x0 to xk minus 1, this term will be 0. And actually, this formula, this is written just in short form. It means that the polynomial pk minus 1, polynomial pk, polynomial of degree k, interpolates the data that pk minus 1 interpolates. Because the values of the polynomials are the same at the points, because it equals plus 0. So the values are the same at the points x0, x1, x2, and so on. But the values are the same for the points from x0 to xk minus 1. And we skip the last point. Now let's consider coefficient c. And let's find the coefficient c from the last condition. And the last condition tells us that pk of xk equals to yk. Xk, yk is the last point, and from this condition we can find the coefficient c. I just substitute the value of xk in this formula. I substitute the value of xk in this formula, and I get this equation. In this equation, these brackets are not zeros, because here I substitute xk, and I have xk minus x0, xk minus x1, xk minus xk minus 1, no zero. And this equation can be solved for c. I can find c. What is the value of c from this equation? C equals to yk minus p k minus 1 at the point xk over xk minus x0 and so on xk minus xk minus 1. The theorem is proved. So we prove the existence of this polynomial, and we prove the unicity of this polynomial. So the interpolating polynomial of degree n exists and unique. But the question, how to find it? We know how to find the linear polynomial, how to find the line that passes through these through 2 points. Now the question is how to find for example, the polynomial of degree 2, the polynomial of degree 2 that pass through 3 points. And the answer is written here. The answer is written here in the form of so-called Lagrange interpolation theorem, Lagrange interpolating polynomial. Let me first read this theorem, and after that I explain it. If x0, x1, and so on xn are distinct real numbers, and f of x is a function, those values are given at these numbers, then a unique polynomial of degree at most n exists with the property p of xk equals to f of xk for all k between 0 and n. And this polynomial can be written in the following form. P of x equals to f of x0 times L0 of x plus, here it's skipped, f of x1 times L1 and so on, f of xn times Ln. This is the same sum in a short form. And here it's written how to find the polynomials, these auxiliary functions Lk. N is written here just to indicate the degree of the polynomial L, the function L, and K is used here to indicate the point that used to build this auxiliary polynomial. How it organized, how to write this polynomial. Suppose that we select some number k, and we should write here all the brackets in the form x minus x0, x minus x1, and so on, x minus xk minus 1, and we should skip the point xk and continue x minus xk plus 1, and so on, x minus xn. And here we should use xk minus x0, xk minus x1, and so on, xk minus 1. Then we skip the point k and continue xk minus xk plus 1, and so on, xk minus xn. Well, this is a general form for any degree, for any n. Let's consider the partial case, the particular case, that n equals 2. If n equals 2, it means that we have 3 points. The points with their numbers 0, 1, and 2. Again, suppose that n equals 2. N equals 2. It means that we have 3 points. x0, x1, and x2. N equals 2. x0, x1, x2, and 3 values. F of x0, f of x1, and f of x2. For shortness, sometimes I will denote it as just f0, f1, and f2. 3 points. N equals 2. Using this general formula, we can write a polynomial of degree 2. E2 of x. How to write it? According to this formula, I should write f0 times L0 of x plus f1 times L1 of x plus f2 times L2 of x. I just rewrite this formula on the board for n equals 2. F0, F1, F2 are constants, are given numbers. Now the main question, how to write L0, L1, and L2. I should use this notation. How to write L0? L0, according to this general formula, if I write Lk, I should skip the point k. When I write L0, I should skip the point 0 here, and I should use the point 0 in I should skip it in numerator and use it in denominator. L0. I skip the point 0 and I write x minus x1, x minus x2 over k equals to 0. K equals to 0. X0 minus x1, x0 minus x2. How to write L1? How to write L1? The same idea. The same idea. I should skip the point 1 in numerator and use it in denominator. I should skip the point 1. So I write x minus x0, x minus x2 over x1 minus x0, x1 minus x2. And the last function, L2. L2 of x. Here, k equals 2. And I should skip the point to x minus x0, x minus x1 over x2 minus x0, x2 minus x1. After that, I can substitute it into this formula and get the final answer. You see that the approach is similar to the approach that we used to find a polynomial of degree 1, just the formula looks more complex. But before we try to apply it, let's try to compute as in previous case, as a case for polynomial of degree 1. Suppose that we write a polynomial in this form. What will be P2 of x0? P2 of x0. How to compute the value of the polynomial P2 of x0? We should substitute x0 into these three formulas for L0, L1, and L2. When we substitute x0 here, what will be the answer for L0 of x? L0 of x0. So again, we are going to find P2 of x0. What will be L0 of x0? Right? You substitute x0 here, it's 1. L1 of x0, L1 of x0. It's very simple. L1 of x0. If you substitute x0, it's 0. 0 because this is 0. It's 0. L2 of x0, 0. So we write these functions L0, L1, and L2 in such special form that gives us 1 for this point and 0 for other points. So we have 1 times f0 plus 0. So actually it equals to P2 of x0 equals to f0. And the same situation will be for x1 and x2. If you substitute here x1, imagine that we substitute x1, 0, 1, x1, 0, 0, 1, 0, and P2 of x1 will be f1. If you substitute here x2, 0, 0, 1, and P2 of x2 will be f2. So we organize this function in such a way that the value of the polynomial of at the point x0 equals to f0, x1, f1, P2 of x2 equals to f2. So this polynomial will be interpolating polynomial, that it passes through the points. Well, to understand how it works, let's try to implement it. Suppose that, let's consider the same data, but let's take first 3 points. First 3 points. The points are 0, 2, 3, and the values are 1, 3, and 2. x0, x1, x2, f0, f1, f2. The task is the same as on previous. Write a polynomial of degree 2. Write a polynomial of degree 2 using this form. The form of Lagrange interpolating polynomial. P2 of x. How to do it? You should first write the formula for L0, for L1, for L2. You should substitute here the values x0, x1, x2. And after that, substitute it into the first formula. Well, also Wait for a minute. I share again, not a presentation, but I share another screen. If you type in Wikipedia Lagrange interpolation polynomial, not in Wikipedia, in Google, the first page will the first link will be the link to the Wikipedia, and you see the same picture, more or less the same picture that I draw during this lesson, different polynomials, and the problem statement is exactly the same. You have the set of k+1 data points, and you find some function. This is a formula. This is a formula that we already write x minus x0 and so on. This is a formula for the LGX. I don't know, is there some examples? Yes, and example for how to find a Lagrange interpolating polynomial of degree 3 and so on. Well, all the information, if my presentation is not, you find it not very good, you can find it in Wikipedia or in any book of numerical analysis. Well, let me show you my presentation again. So I ask you to take these 3 points, the first 3 points, and find Lagrange interpolating polynomial for these 3 points. do it step by step. What we find the formula for L0?
X squared minus 5x.
X
X squared minus 5x.
x squared minus 5x. And again, we can check this result if we substitute. I think this result is wrong because
X is x comma 5x plus 6
plus 6 x squared minus 5x plus 6
yes over 6
over 6. Yes, this result seems correct because if you substitute here x0 equals to 0, we have 6 over 6, 1. So this is what, if you substitute 2, we have 4 minus 10 plus 6, 0. And if you substitute 3, 9 minus 15 plus 6, 0. Right, this is correct. L1 x squared minus 3x over minus 2. I don't know. I don't. It seems correct. It seems correct, and also it's very simple to check. If it's L1, if you substitute here, 0, you should get 0. If you substitute here 2, 1, and 3, 0, right? And the last term, L2,
X squared minus 2x over 13.
minus 2x over 3. Maybe, I don't know. Again, it's very simple to check when you substitute 0, 2, and 3. Well, and after that, you should substitute all of these terms into the first formula and find P2 of x. P2 of x. Of course, you should carry out some simplification. Well, about no. Okay, as far as here we have six. It's better to write this fraction as yes times 3 over 6, and here times 2 over 6, and after that simplify it.
S for being 3%.
What?
S for being 3%.
Well, I think some mistake. Again, if you put 0, you get 1. Okay. If you put here 2, the answer must be 3. According to this data.
So the final answer is not 1.
The final answer must be polynomial.
Yeah.
Why you tell me 1, 2? It's not a number. It's not a number. It's a polynomial. It's a polynomial of some degree.
Okay.
It must be a polynomial of some degree.
Okay. Answer each other. Must be.
Why use x here? No. No x. Why x? It's L of x. It's L of x. No x. No x, but all other is correct. Over 6, yes. But if you write it, it's not over 2. It's over 6. If you 3, okay, but 3 x squared, not x2 but x squared. Here 9, you lose x. It's not x squared minus 3x. You lose x, please, sir. 3 over 6, right? And here 2 over 6, okay. But here's x squared minus 5 plus 6, plus 6, okay. Here 3x squared minus 9, but here you get minus 6. Here minus, so you should write here minus 3 plus and 6 2x minus 4. This is a mistake, you forget this minus. So, carefully check your computations. Don't forget the minuses, all the minuses, all the numbers.
I think it must be
The final answer must be very simple. not very large formula, just a short formula. No. Somewhere, I think, maybe I don't check the last one. The last one is correct or not? If you put 0, 0, if you put 2, 0, 3, 9 minus 6, yes, 1, okay. Okay. Because it's x squared cannot cancel each other. Oh, you forget times 3. So well, you forget F2 and F1. F0 now. What is F0? 1, okay. What is F2? 3. So you should yes, multiply these. Three. And the last 2. So these 3 and 2 are not this
Yes,
F.
yes.
It's just to have the same value in the numerator. This one. Okay. First, okay. First, can say that it can be, I cancel 2. I can write it as minus 3 square plus 7x plus 3. Well, and after that, you can substitute the values. If you substitute 0, 3 over 3, 1. If you substitute 2, you have minus 12 plus 14, 5. 5 plus 3, it's too much. I think somewhere made a mistake again. Well, what you should write? What is P2? This times, so this 1 over 6 I can move outside. 1 over 6 I can move outside. L1 x squared minus 5x plus 6. Then L2, don't forget this minus. This minus 3 times x squared minus 3 and times F1 times 3 plus 2 times x squared minus 2x and times F2. F2 is 2. We have 1 over 6 x squared minus 5x plus 6 minus 9x squared 9x squared plus 9x squared plus 27x, and here are 4x squared minus 8x. And finally 5x squared minus 9, 4x squared, x minus 5, 27, and minus 8. We have 22, 14, minus 14. Minus 14x plus 6. Over 6. Well, if we put 2, if you put 0 here, 3 over 3, 0, 2. We have here 8 minus 14, 8 minus 14, 6, minus 6, minus 6 plus 3,
9.
I think maybe
It's minus 2x squared plus. It's minus 2x. It should be minus 2x squared plus 7x.
plus 7x.
Yes.
Where is
On the last answer, it should be minus 2x squared plus.
well? Let's check. Maybe I forget
It
The
should be
minus.
positive 9x squared, but you wrote minus 9x squared.
Yes, because it's 27 minus
Yes, then.
set minus 5x minus 8x. It's plus.
Oh,
Minus x squared.
yeah. No, that's plus. Yes, I see. Minus. Yes, right. Thank you. Minus. Mhm. Well, when we substitute, let's substitute 2. Minus 8 plus 14 plus 3, 9. 9 over 3, 3. Let's substitute 3. 9 times 2, 18 minus 18 plus 21 plus 3 over 3, 2. 6. So this is the final answer, the correct answer to this problem. This is a interpolating polynomial. Polynomials that pass through these points. If you substitute 0, you get 1, 2, you get 3, 3, you get 2. You see that it's not very hard, it's just, you should just carefully don't forget all the minuses, don't forget all the coefficients, and if you perform all the computations, it will be, you get the correct answer. Questions? No questions. Okay. Sure. And again, as a home task to understand how it works, again, I ask you to take these 3 points, these 3 values, and do the same. Find the polynomial of degree 2 that pass through these 3 points. The same computations, but please use another points. Next week, we will continue. We discuss about the error of this approximation, because this table of data is not arbitrary table. It's some values of it's the values of some function. But what function interpolates this polynomial? So what is a mistake? What is an error of interpolation? We discuss about the error of interpolation, and we consider one more approach to find interpolating polynomial. Maybe a more simple approach, and this second approach can be used to write interpolating polynomial using computer. It's very simple to do. We don't write in the program. I just showed you some example. But we discussed about it. And next week, our lesson starts as on this week on 9 o'clock, 9:10. We have 2 lessons, and we finish this topic. Questions? No questions. Well, I will send you the presentation. I will send you the video of this lesson. Well, let's finish our lesson for today. Next week we meet at the same time, 9:10, and we will have 2 lessons. Goodbye. Let's finish our work. Let's finish our lesson.